Okay, so I've been instructed or asked to work this web work problem. Given this formula, and we are asked to find, I don't know what we're asked to find, omega, since that's the only thing that we haven't been given. Where omega is called the angular velocity or the angular speed. Typically, we find omega by converting revolutions to radians, but we weren't told any revolutions. We were told that it takes 12 seconds for this particle to move along a circle of radius 4/3, a distance of 8 meters, 8 pi over 9 meters. So the picture that goes with that is we've got this circle here, and it's covered 8 pi over 9, which is almost 1 pi. So it's going a little bit further down to here. So there's our S. And some angle starts out here and then traces to here. That's going to be the angle theta, which we're not given, but we are given that the radius is 4/3 meters. And typically omega is the radius, I'm sorry, the angle traveled, the angle traveled divided by time. And so what they did with this is they solved for, and S is R times theta. Well, what they did is they solved this equation for theta and got theta is omega times T, and then put that in where the theta is. So we're going to try to solve this equation for omega. So I think it's just a matter of substituting things in here. I've got S is 8 pi over 9. And now my equal sign, my radius is 4/3 meters. Omega is what we're looking for, and T is in 12 seconds. So we're going to work to solve this for omega. First thing I see is that I'd like to divide that 12 by the 3 down there. So let's take this 3. 3 goes into 12 4 times. Then those two 4s can multiply together to give me 16. So I have 16 omega is equal to 8 pi over 9. So now I'm going to divide both sides by 16. I'll write it like this so you can see where I cancel. And then 8 goes into 16 twice. So I get pi over 18 as omega. And that's going to be in units of meters. I think time was in seconds. Well, radians, since it's an angular measurement. So try entering that and see if it works. If that doesn't work, then enter a decimal of some version. Does that make sense? Yes. In the same web work, number 15. See if I can find it. Okay, number 15. Let's see, we've got a satellite traveling approximately 2,200 kilometers above the Earth. Takes 7 hours. Come on, get out of the way. To make one orbit. For this problem, you can decimal answers, whatever that means. Be sure to give several digits. Okay, so let me kind of paraphrase this. I guess we have to use the fact that 6,400 kilometers is the radius of the Earth. So we've got the Earth here with a radius of 6,400 kilometers. Some satellite is rotating around the Earth at a distance of 2,200 kilometers. Oops, I'm going to need to get all these numbers. Let me write this down and then I'll switch it back. Let it take 7 hours to make an orbit. I want the linear speed and the distance in 5 hours. Okay, now I can switch it back, I think. Which would be maybe here. There we go. Okay, so here's the problem paraphrased. We've got this satellite 2,200 kilometers above the Earth, whose radius is 6,400 kilometers. It takes 7 hours to make an orbit. We first want to find the linear speed. And then once we have that, we can figure out how far it travels in that time period. And we can use that 7 hours to make an orbit to find the angular speed. And then the linear speed, if you remember, is just r times that angular speed. So linear speed, v, is equal to r times omega. To get omega, we're going to use this. We're going to convert an orbit into radians. So it takes 7 hours for one orbit. Oops, I want time units on the bottom. Time units on the bottom. I got that upside down. In speeds, linear and angular, the time units are always the denominator, right? We're going to do per hour. So it takes 7 hours to make one orbit. So to get the angular velocity, I convert that now. I make 2 pi radians in one orbit. So it takes 2 pi divided by 7 radians per hour. That's the angular speed, 2 pi 7 radians per hour. So if I take that now and multiply by the radius of the satellite, we'll get the linear velocity. To get the radius of the satellite, add the radius of the Earth with the distance that that satellite is above the surface of the Earth. So here, the radius is 2,200 plus 6,400. So I think the radius of the satellite is 8,600. So take that, multiply it with omega, and I get radius 8,600 times 2 pi over 7. I don't think that goes evenly, so let's just multiply that out. Maybe 17,200 pi over 7, and that's going to be now in kilometers per hour. And so if we know the rate that this object is traveling, we can find the distance that it travels just by multiplying distance is equal to rate times time. So take our rate and multiply it by the elapsed time. In the second part of this problem, the elapsed time is 5 hours. So distance is what they're calling S, is equal to our rate times our time. So our rate was 17200 pi divided by 7, and then we just multiply that by 5. and that's going to be in units of kilometers. So I don't know if this is going to take decimals or if it will take this exact answer. We can give it a shot. So make you a little sheet with the formulas on it. Omega is theta divided by T. S is, I'm sorry, V is R times omega. Yes. You good? Okay, so we're looking at what this number 8 is.
And the other equations that they can use just come from those equations.
Yes, yes. So the ones that I've been saying is, so our formulas that we use over and over again, that omega is theta divided by T, but I hardly ever use that because I can always find the angular velocity by converting revolutions into radians, right? Take how the time that it makes a revolution, multiply it by 2 pi, and that's omega. And then the angular velocity was either S divided by T, but S is R times theta, but theta over T is omega. So that's what we're using over and over and over and over. Some version of this depending on what we're given. Okay, so I gotta look at number 8 and 3334. Okay. Get over there. Don't get over there. That would be here. 8. Okay, so let me kind of copy this down and then I'll switch it back to the screen. Suppose a point P is on a circle of radius R is 30 centimeters and ray OP is rotating with angular speed of pi over 10 radians per second. So draw a picture. I'm just drawing a circle and I'm going to label its radius 30 centimeters. O is the origin. P is a point on the circle. Is rotating with angular speed of pi over 10 radians per second. Find the following when T is 6. We want angle generated. We want distance. P has traveled along the circle, so the distance is given by arc length. And then we want the linear speed. That's what we label V. So I'm going to change the angle, the notation to us. All right, let me get back to that. And here is the problem. I drew a circle of radius 30 centimeters. And then omega was given as pi over 10. And we want to do all of the following things at time T is equal to 6. Find angle theta. Okay, so let me pop this formula sheet back up here. I'm going to use this first one to find angle theta. We've got omega and we've got T. So I'm going to use it to find theta. Then when we want to find the distance, I'm going to use my distance S is R times theta. S is R times theta. And then for the linear speed, I'm going to use linear speed as R times omega. Okay, so to get angle theta, I'm going to use omega is equal to angle traversed divided by time. To get S, I'm going to use S is equal to R times theta, and linear speed V is omega times R. I just wrote it backwards, so I hope that doesn't bother you. That's my plan. So theta is pi over 10, t is 6 seconds. So omega is pi over 10. T is equal to 6 seconds. So to solve that for theta, I'm just going to multiply both sides by 6 and get theta is equal to 6 pi over 10. And if you want to divide out a 2, that gives me 3 pi over 5. Okay, so that's going to be in units of radians. Now we're going to use that to find the distance traveled. So it's going 3 pi over 5 radians on a circle of radius 30 centimeters. So I just multiply those two together. S is equal to 30 times 3 pi over 5. And let's see, 5 goes into 30 6 times. 6 times 3 will give me 18 pi. That's a linear measurement, so that's going to be in centimeters. Next, yes.
It's number 14. It's the minute hand of the clock. If you put the
Okay.
omega for it.
Okay, I'll do that. I've got one more part to this one that's hidden down here. Let me catch up with that. Okay, so the linear speed then is the omega that we were given, pi over 10, times the radius that we were also given, 30 centimeters. So our linear speed is just 30 times pi over 10. The 10 divides into 30 and leaves me 3 pi, and that's now a linear speed. So that's going to be a centimeters per second. Does that make sense to everybody? So it kind of helps to have your formulas written in front of you, and you can kind of look at what's given. Well, the thing that was kludgied up about this problem is they use different letters for their linear speed than we do, and different letters for the arc length and things like that. So just got to learn how to speak through different translations of the same topic. Okay. All right, and do you know which web work number this one is?
14C.
14C. You want to read it to me?
It's the minute hand of the clock. And it's the omega in radians per second.
I'll need the radius of that, or the length of minute hand.
That's all it gives you.
Okay, you got the minute hand of the clock, and we're supposed to find what?
Omega.
Find the angular speed. Okay, so we don't need to find the velocity, we'd need the radius, but not for omega, right? The minute hand of a clock makes a revolution all the way around the clock, right? One revolution takes how long? 60 minutes. So that's the way we're going to compute this, that it takes one revolution of the minute hand takes 60 minutes. So I said, if you want to convert that to omega, you just multiply it by the fact that 2 pi radians is the same as 1 revolution. And so we multiply that by 2 pi, and we get omega to be 2 pi divided by 60, which reduces to pi over 30 radians per minute.
Yeah, it's wrong. Whoever-
Web work is wrong.
That's where I got it first.
Does it want the units on it?
It took, because the second hand of the clock, it took my pi over 30 for that one. And with the minute interval, it won't take that one.
Read further and see what kind of units it wants.
It just says radians per second.
Well, I've got radians per minute. So now we've got to convert radians per minute into radians per second. Okay, so find omega in radians per second. So here I've got it in terms of radians per minute. See, I've got it going 60 minutes around. So now we've got to multiply that by however many, our conversion factor for minutes and seconds. And so we know that 1 minute is 60 seconds. I want minutes to cancel, so I'm going to put 1 minute up here, and I'm going to put 60 seconds down here. And then the minutes cancel, and you see how we're left in radians per second. So we've got to take our pi over 30 and multiply it by 1 over 60. 3 times 6 is 18, tack on 2 zeros there, and we get pi over 1800 radians per second. It should take that. Okay. And that's typically how I'll find omega. Transfer the revolutions per time period into radians per specified time period. Okay.
Is that the cheat problem most students have with those problems? I've noticed that I have been that set a lot of times.
About not putting it in the right units.
No, not the right units. It's not really that an issue. I was trying to just learn and show you those original equations,
Uh-huh.
and I realized I was not in the right boat at all when I was tutoring. And when we started doing that, I was like, I don't know how to start doing that.
It does depend on what's given. And so nowhere in here have we been given the angle itself or the amount of time. That one question said it moved an angle of so many radians in 6 seconds. So we could use that to get omega. But more often than not, it tells us how long it takes to make a whole revolution. So it does depend on what's given. Yes, sir.
Would you go over 3.3.4
Problem
problem 4?
4. Okay. Okay. Number 4. Will it fit there? What am I going to find? Cosecant of 13 pi divided by 3. Okay, cosecant of 13 pi divided by 3. So I'm going to find the sine of that because cosecant is 1 over the sine. That means pi over 3 is our reference angle. Does anybody know the sine of pi over 3? Square root of 3 over 2. Now I've just got to figure out which quadrant 13 pi over 3 is in. Sine is positive in quadrants 1 and 2. So I'm going to get 1 over that number if this is a quadrant 2 angle. I'm going to get negative 1 over that number if this is a quadrant 3 or 4 angle. How can we determine which quadrant this is in? That's right. This is more than 2 pi, right? 3 goes into 13 more than twice. So let's see how many laps around the circle it is. I'm going to take 13 and divide it by 3. Well, 3 times 4 is 12 and leave me 1/3. So 13 pi over 3 is the same as 4 pi plus my remainder 1/3 pi, which is just pi thirds. So if you start forming this angle, you've got to go 4 pi, which is 2 complete laps around the circle, and then 1/3 pi more. So which quadrant does this put you in? 2 laps and then 1/3 more. So it's in quadrant 1, isn't it? And the upper half of the circle, 1/3 pi is in quadrant 1, 2/3 pi is in quadrant 2, 4/3 pi is in quadrant 3, 5/3 pi is in quadrant 4. So this is a quadrant 1 angle, which means my answer is going to be positive. So all I've got to do now is take 1 over the square root of 3/2. And when I do 1 over a fraction, it flips it over. So I don't know if it wants it rationalized or not. That answer is fine for me. But if it wants it rationalized, multiply top and bottom by the square root of 3, which would get rid of the radical on the bottom, but put a radical in the numerator. Is that okay with everybody? Take it over a little bit. That way? Oh, a little bit more. There we go. Okay, when's the next exam? I think it's this afternoon, isn't it? What, we having another test today? No. I think October 19th. October 19th is the next exam. Getting antsy, are we? We just had a test. My hand's still cramped from grading. Did you have one?
Yeah, can we go over number 4, section 4.1?
Number 4, section 4142. Ha ha, there's a little peer pressure. We got somebody in chapter 4. .1, 4.2, number 4. Can you tell me what it is, or am I gonna look it up?
It's a picture of a graph and then the signs. I don't have that.
Okay, maybe I should do more on that section first. Let me take a quick look. Let's see, that would be here. Okay. Let me talk a little bit more and then let's come back to this one if that's all right with you. So are we done with the other stuff? Are we done with the other one? I'll come back to this one. So let me give you an overview of what we were doing in sections 4.1 and 4.2. We're going to take the graph of y is equal to the sine of x, y is equal to the cosine of x, and talk about what happens if you put a number in front of those two trig functions, and what happens if you put a number in front of the x. That's what we did last time. The basic graphs of sine and cosine. We are working toward these two forms. F of x is equal to a number times the sine of bx plus c plus another number d. Or g of x is equal to the cosine with all those same placements of letters. That's what our goal is today. If we know the numbers A, B, C, and D, what do the graphs look like? And they are some version of the graphs of our apparent functions, sine of x and cosine of x. So let me remind you what those look like through one period. One period of both of these trig functions is the interval from 0 to 2 pi. That's how long it takes these trig functions to complete one of their cycles. So we took the points on the unit circle from 0 to 2 pi, and we plotted those angular measurements as our x-axis, and then the particular output of those angles as my vertical axis. And we got these two graphs as the basic parent graphs. I'll draw them all through one period. And I'll draw one period on each side. Okay, so first I'm going to graph f of x is equal to the sine of x. And I'm going to put 2 pi right here. And then just start cutting these intervals in half. So that would be 1 pi. And this will be pi over 2. And this would be 3 pi over 2. I'm going to make this 1 unit tall so that my scales don't agree. And 1 period of the sine curve. Sine of 0 was 0. Sine of pi is 0. Sine of 2 pi is 0. Sine of pi halves is positive 1. And sine of 3 pi halves is negative 1. And so if I draw the curve through here, concave down here, begins to bend concave up, and that's 1 period. This graph goes on forever and ever in each direction, simply by picking that up and hooking it on endpoint to endpoint. So if I go back to negative 2 pi and put my half pi's here, then I'm going to be down 0, up 0. So here I'm going to draw in pencil what 1 more period looks like so that you can compare and see that that's just the same graph hooked end to end. And I can do that forever in each direction. So you got to remember the sine starts at 0, 0, goes to 0, pi 0, goes to 2 pi 0. Cosine does it the opposite way. Cosine starts at 0, 1, hits pi over 2, 0, pi negative 1, 3 pi over 2, 0, 2 pi positive 1. So the cosine graph will look like this. Trying to be pretty for you guys. All right, so again, I got pi, 2 pi, and 2 of those little slashes are going to be 1 unit. And there's pi halves and 3 pi halves. Draw this in red. Cosine is 1 at 0 and again at 2 pi. It's negative 1 at pi, 0 in between. And then it does a little bending, a little concave down action. Now it becomes concave upward and then concave down. So it looks kind of like a big old smile right there. And the rest of the graph looks like the same thing, picked up and hooked end to end to end to end. So if I draw one more cycle back here, it's going to cross again at the pi halves. It's going to hit the negative 1 here and the positive 1 there. The distance between the top point and the smallest point divided by 2 will be called the amplitude. So the amplitude is equal to max minus min divided by 2. For these basic graphs, the max is 1, the min is negative 1. So 1 minus a negative 1 is a positive 2, divided by 2 is 1. The period has length 2 pi, and the amplitude is 1 in the basic graphs. So up here in our convoluted looking formulas, the number A is going to change the amplitude. That's a stretching factor, just like it does with any graph. And the number B is going to change the size of the period. So let's just look at those two factors. down. More. So f of x is equal to a sine of bx, or g of x is equal to a cosine of bx, without the other numbers around them. The number a in absolute value is going to be called the amplitude. And the number b is a factor that's going to change the size of the period. The period is going to be the original size of the period divided by that number b. So if b is a number bigger than 1, the period gets shorter. If b is a number smaller than 1, the period is going to get longer. If a is a positive number, the graph stays in its orientation but is stretched taller. But if a is a negative number, it flips over first and then is stretched. So if that number a is negative, the graph is flipped. For example, the graph of y is equal to 4 times the sine of x looks just like the graph of the sine of x, but instead of this point going between 1 and -1, it goes between 4 and -4. It's just much taller. And so if we draw one period of that, right here, let's say this now is 4. I got to go down a little bit, hit me -4. That was 3 slashes there. Let's make that pi, 2 pi, and then cut those intervals in half. It's a sine curve, so I know I'm going to pass through those points, 0 pi, 2 pi. And then here I make this 4 units tall at pi halves, -4 units tall at 3 pi halves. So it looks exactly the same. It's just taller. The amplitude is now 4. If I want to graph on top of this, g of x, I'll use g, let me use just f of x is equal to -1/2 sine of x, then 2 things have happened. The first thing is that I have to flip this graph over, and then I make it half as tall. The amplitude is a half. So I'm going to draw this one in red on the same coordinate system because I haven't changed the period any at all. I've just flipped it over by multiplying by a negative number, and I made it half unit tall. So if this is 4, then that's 2, and so 1 is in here. So let's make this a half right there. I don't know why I chose a half. Let's go 3 halves so I can see it. So let's make the amplitude 3 halves. So let's see, I said that's 1, 2, 3, 4. So 3 halves is going to be about right here. Let's put our peak at 3 halves in red. And if that's 3 halves, then that's going to be a -3 halves. Down here. Shape stays the same. Oops, I got to flip it. I didn't flip it, did I? So in red and dashed. How about that? So now I'm going to flip it. So now I take this point down to -3 halves. right here. That point goes to positive 3/2 here. And there's the flipped graph. Right there. Now, the one on Webwork was very similar to that, I think. Let me take a quick peek. Okay, that's got a change in the period. So let me go do a change in period first. Putting a number in front of the X changes the period. So let me show you what that looks like. F of X is equal to the sine of 3 times X has a new period. The amplitude is 1. Because I didn't stick a number in front of the sine curve. But the period now, remember, is 2 pi divided by the multiplier of X. Two pi divided by 3 is the period. It takes a length of 2 pi thirds for this sine curve to complete its up, down, up cycle. So when I draw that, I'm going to let's draw the first period again. Okay, so if this is pi right here, and I cut that into 3 equal pieces, the second of those 3 pieces will be 2 pi thirds. So in this little bitty tiny interval, this trig function is going to do its up, down, up motion. So I know my sine curve begins and ends its period on that horizontal axis. That's why I covered this dot in. It's going to begin here, and then at the halfway mark, it crosses again, since it's a sine curve. The halfway mark was 1 pi third. It hits its max and min in between. So if I want to find out what's halfway in between 0 and pi thirds, I just take pi thirds and multiply it by half. Half of pi thirds is pi sixth. At pi sixth, it reaches its maximum height. So let's say this is 1 unit, and there's its maximum height. So it should reach its minimum height in between pi thirds and 2 pi thirds. So that's going to be some version of a pi over 6. Let's average those two numbers. Add them together and divide by 2 to figure out the coordinate right here. So pi thirds plus 2 pi thirds divided by 2 is going to be the coordinate right here. Pi thirds plus 2 pi thirds is 3 pi thirds. So that's pi. That point right here is pi halves. Well, that pi halves, I said. That makes sense because if I have these blocked off in increments of 1/6 pi and just count, this is 1/6 pi, 2/6 pi, 3/6 pi, and 4/6 pi. I've got everything going right where I need them. So at pi halves, it's going to hit its minimum at -1. And then it does its sine curve thing. So you got to make yourself a scale big enough that you can see. And when you're drawing these graphs for me, I want the intercepts labeled and the place where it hits the max and min labeled. So I want the points that I've labeled right here. Yes, sir.
Go from 2 pi thirds, finding all 4 of those points. Can you just take 2 pi thirds, divide it in half,
And then divide it in half again. But then to get that other half, I just averaged those 2 endpoints. My other 2 endpoints were at pi thirds and 2 pi thirds, so I averaged them to get the other half. I could have done that counting thing and just counted by pi sixth. But you're right, get the three intercepts for the sine curve, and then cut those intervals in half to get the max and mins. Okay, so let's do one of those phase shifts with the cosine curve. You have this one written down already? My next example, let's look at g of x. All right, let's make an upside down cosine curve. So let me put a -2 here. And then cosine of, say, x divided by 2. And so I make the note that the minus sign is going to flip the graph over. The 2 itself is going to be the amplitude. And the number in front of the x, x over 2, is the same as 1/2 times x. So that 1/2 is the b. The period is 2 pi divided by b. So if I take the 2 pi and divide it by 1/2, I flip and multiply and get a period of length 4 pi. So I've got to draw an upside down cosine curve. It begins at 0, -1. It ends at 2 pi, 4 pi, -1. And then get the symmetry to get all the other points in between. So I'm going to take this cosine curve here. I'm going to flip it upside down so that it's going to make that little upside down loop. I'm going to label this point as 4 pi and then this point as 2 pi, and we'll cut the intervals in half. And so here she goes. All right, it's got an amplitude of 2. So let's make this a 2 right here, and that a -2. Let's label this point as 4 pi. Go halfway in between and label that as 2 pi. Then go halfway in between that and get 1 pi. And so this looks like it should be 3 pi. It's upside down. So remember I said I'm going to start it here and I'm going to end it there. And the point smack dab in the middle was the 2 pi. That's going to be up here. The other pi's are going to be where it has intercepts. And then we'll draw it concave up, concave down, and concave up. Okay.
So on the webwork, I haven't started it yet, but do we don't have to graph it all? It's just us showing like the amplitude and stuff.
There's some where the graphs are given and you have to decide what's going on with the graph. So let me take a quick peek at this one again and see if we have enough information to see what's going on with this graph. Okay. So that doesn't look like one cycle, right? If it's starting up here at 0, 3, then I'm thinking cosine curve. But that only looks like half of a cycle, right? That only looks like we're going from here to here. So that's not the entire period. So let's take a look at how we would do that particular thing. Let me draw that graph and then I'll put my screen back on and to get you guys to thinking about how are we going to write this equation. And so I'm thinking we're going to use a cosine curve, and it says find the positive number b that does that And then we're also going to have to find that number A. So I want you to think about why that's a cosine curve. Draw it over here. Goes through 0, 3. It goes through pi, 0. And then at 2 pi, it's at -3. All right, let me flip it back to my screen. So I think that's the problem right there. And we're supposed to come up with some version. I know it's cosine. Come up with the numbers A and B. But that's not one cycle of the cosine. That's only going to be half of a period. Because it doesn't look like an entire cosine curve. So if half of a period takes me to 2 pi, one whole period is going to take me to 4 pi. So it's going to do this again out to 4 pi. So if I know my period is equal to 4 pi, I can figure out B. And I know my amplitude. This goes between 3 and -3. So I know my amplitude A, they're using a lowercase a in this example, is 3. Now remember, period is given by 2 pi over the number in front of the x. So I'm going to solve this equation for B. 2 pi divided by B is equal to 4 pi. And so if I cross multiply, I get 2 pi is equal to 4 pi B. Now divide by 4 pi, and I get B is equal to 1/2. So this is the same function that we just drew, except for a different amplitude. The graph of this function is f of x is equal to 3 cosine of 1/2 x. Is that too fast? Yes, sir.
Is there a difference between f of x and cosine? Should you actually put-
No, I'm just trying to label them so that we can call them whatever per example. This problem used f of x, so that's why I wrote it that way. Okay. So you gotta look for your basic shape and then figure it out from there. And I'm gonna make it harder for you because now I'm gonna take that basic shape and I'm going to move it left or right. And to move it left or right, we're going to add a number inside here. When there is action done inside the rule, that's affecting x's. When there's action done outside the rule, that's affecting the y's. So putting a number here is going to pick the graph up and move it left or right. Our trig functions start when the stuff inside the parentheses is 0, and they end when the stuff inside the parentheses is 2 pi. So if I take this stuff inside here and set it equal to 0 and solve for x, bx plus c is equal to 0. Solve that for x and you get x is minus b divided by c. That ratio minus b divided by c is going to be called the phase shift. I'm on page 6. Now consider f of x is equal to a sine of bx plus c, or g of x is equal to a cosine of bx plus c. Remember that this number is the amplitude. 2 pi divided by b is the period. And our periods now are not going to begin at 0. This shifts it away from 0. So if I take bx plus c and set it equal to 0, then the ratio x is equal to minus c over b is where the period starts. That number, that ratio is called a phase shift. Minus c over b is the phase shift.
How would that equation work? If there's no-
Let's do it. Let's just go and graph. I still like doing sine curves. So let's graph two functions together. Let's graph f of x is equal to the sine of x plus pi. And let's also graph g of x is equal to the sine of, pick a number. We did a 2x plus pi. So here I had b is 1, here I have b is 2. But in both cases, c is pi. So when you see sine, you're thinking the sine curve, like that. 0, 0, up to 0, 2 pi 0. But we're going to change. This one still has the same period. B is 1. So the period is 2 pi, but this one, B, is 2. So the period is 2 pi divided by 2, or pi. It takes a length of pi to do one cycle of this particular sine curve. Here, C is equal to pi. So the ratio minus C over B becomes minus pi over 1, or minus pi. The minus sign is going to indicate that it picks the graph up and moves it to the left, pi radians. So the shift is to the left. Move everything over pi. This one has a phase shift of minus C over B. And we said C was pi, B was 2. So minus pi over 2. This one goes to the left, pi over 2 radians. Typically, when a number is added, the graph goes left. When a number is subtracted, the graph goes right. It goes backwards in the x direction. I'll graph this one here. I'll graph this one over here. So I'm going to need to move it. Okay, so it's still got a period of 2 pi. Let's make this length 2 pi. It still has an amplitude of 1. So let's make this unit 1. I'm going to draw the sine curve that's not been shifted with a dotted line. So here's the not shifted sine curve. Where these are at pi halves. So the dotted is just graph of the sine of x. Now I'm going to pick up these points and I'm going to move each of them pi units to the left. So I'm going to take this point from here and I'm going to move it back to here. So that's point number 1 has been moved to here. I'm going to take this point here and I'm going to move it pi units left. So that's, I got to get a pi halves back here. So pi halves minus pi takes me to negative pi halves. So that point has been moved to there. Take this point and move it back pi and it goes here. Take this point and move it back pi and it goes to here. And then this point back pi goes to here. And so now I'm going to draw it in red. See how those points have moved? Take pi halves and subtract pi and you're back at negative pi halves. Take pi and subtract pi and you're back at 0. So I'm moving these dotted points back pi units. Seem like it's shifted correctly to you? This next graph is going to essentially look the same, but I'm going to shorten the period. My period now goes to pi, so that dotted graph, instead of ending at 2 pi, is going to end at pi. Then I've got to pick it up and move it pi over 2 units to the left. So I'm going to draw it. The period is a dotted graph, and then I'm going to move it pi over 2 units to the left. So let's draw that one down here. I'm going to draw sine of 2x dotted. And it's going to look like that again, but it's going to end at an interval of pi, right? The period is pi. And so it makes its crossing point halfway between at pi over 2. And halfway between that will be pi over 4. And then this one should be 3 pi over 4 if I just count by fourths. It still has an amplitude of 1. Okay, so I'm going to draw the unshifted graph first. I'm going to draw one cycle of the sine of 2x. It's going to hit here at pi and smack dab in the middle and then do its up, down, up thing. So up, down, down, and back up. So at pi fourths, it hits 1, and at 3 pi fourths, it hits negative 1. Now we've got to take the main points of this graph and move them pi over 2 units to the left. So I'm going to move this point, this one, that one, and that one pi over 2 units to the left. So let's move that one. You can't see the green, can you? Okay, so let me keep my scale. That length was pi over 2. So that's negative pi over 2. Then this is going to be negative pi over 4. Okay, so let's go. Let's move this point pi over 2 to the left. So it ends up right here. Now I'm going to move this point. Let's call this point number 2. That's at pi over 4. So my new version of number 2, I'm going to call 2 prime, which is off my page. To get where 2 prime is, I'm going to take, it starts at pi over 4, and I have to move it left pi over 2. So what's pi over 4 minus pi over 2? Is it negative pi over 4? 1/4 minus a half? So this point I labeled 2 is going to be moved to here. Negative pi over 4. Now this point that I'm going to label is 3. If I move that back pi halves, well, that's kind of easy. Pi halves minus pi halves is 0. So this point at 3 moves to the origin. And then 3 pi over 4, if you just follow the pattern, is going to move back to pi over 4. So point number 4 moves to here. Point number 3 moves to here. And then pi minus pi halves is going to put me to here. And so I'm going to connect my red dots with a red graph, and that's going to be the one that has the phase shift to it. Okay. So it begins its period at negative pi halves and ends its period at positive pi halves. And then the symmetry in between. Okay? All right, we've got one more shift to do, and that other shift is the one that adds a number on the very end. So I'm going to talk about what happens when we stick a number way out here. But if you're going to stick a number way out here, it's not affecting the x, it's affecting the y. Think about what that looks like on the graphs you know. Suppose you have the graph of y is equal to x squared. How does that compare to the graph of y is equal to x squared plus 2? Goes up 2. How about y is equal to x squared minus 5? Goes down 5. That's what that number at the end does. It takes whatever this curve is doing and it moves the entire period up or down d units, depending if d is positive or negative. It follows the sign of d. If this number is positive, it goes up. If that number is negative, it goes down. So that's going to be called, what is this direction? That's vertical. That's going to be a vertical shift of the graph. Picks it up d units. Because it's picking, well, it's going horizontally. I've always called it phase shift, but you can call it a horizontal shift. There are 2 kinds of horizontal shift. One's going to take its period and smush it and not move it anywhere, just smush it. That's the period change. And then the other one is after it's been smushed, pick it up and move it. So a couple of steps in the vertical shift, a phase shift and the smushing effect. Smushing effect is a real technical math term. So finally, this number d at the very end picks the graph up or down d units. Finally. F of x is equal to a, get over there, sine of bx plus c plus d, g of x is equal to a cosine bx plus c plus d. Then the number d is, what do we say it was? This way is vertical. Shift up if d is positive, down if d is negative. So for example, suppose I want to sketch the graph of f of x is equal to 4 sine of x minus 2. So I haven't changed the period because I didn't do anything inside. I haven't changed the x at all. All I've done is change the y twice. I made it 4 times as tall, and then I picked it up and pulled it down 2 units. So I have the amplitude is equal to 4, and then this 2 is that it's moved down 2 units. So like I did before, I'm going to draw it before I move it down. I'm going to draw one cycle of the sine curve with a period of 2 pi. Then I'm going to move it, the important points, down 2 units. Okay, so an amplitude of 4. Let's make this 4. And that's negative 4. Period of 2 pi. So let's put 2 pi out here. Pi in between. And then these would be the half pi's. So the sine curve hits its max at the pi halves, has intercepts at all of the pi's. Now draw a dotted graph through there because I'm about to pick it up and move it. So the dotted graph is just 4 sine of x. Now let's pick each of those y values up and move them down 2. So one of these here is going to be 2 units. So I'm going to do that in red now. I'm going to take it from 0, 0 and put it down to 0, negative 2. I'm going to move from pi halves 4 to pi halves 2. Pi 0 becomes pi negative 2. 3 pi halves negative 4 becomes 3 pi halves negative 6. And then 2 pi 0 moves down to 2 pi negative 2. And I'm going to draw a solid red graph through there to represent this graph. Okay. Drawing them is almost is much more fun, but we should be able to work in the other way as well. And so let me see if I can figure out one that works in the other way. Let's have that. Let me just put this up here, just as our last little 5 minutes, maybe 3 minutes. Okay, let's look at this. Okay, I'm pointing to this one here in A. And if you were to guess sine or cosine, what would you guess for this one? Because it goes through 0, 0, right? Yeah. It has an amplitude of 2, and it comes back to pi. So an amplitude of 2 and a period of pi. And it's a sine. So let's look up here and see which of those has an amplitude of 2, and then we'll see which of those has a period of pi. So that has an amplitude of 2. That has an amplitude of 3. Oh, that looks like a 3, doesn't it?
Yeah.
Okay, so we want the amplitude of 3 in the period of pi. So there's the amplitude of 3. There's an amplitude of 3. The period is 2 pi over b. So this is a 1, right? Agree? Yeah. Look at this one. Looks like a cosine, because a cosine starts at 0, 1 and goes back up. But it only does half of a cycle here. So that's that one that's gotten its period stretched by a factor of 2. So that means it's got to have a fraction in front of the x. The amplitude is still 1, so we want a 1 times cosine of a half x. Agree? All right, so we'll talk about tangents and secants next time. Yes. All right, guys, catch you on the other side.